Hello everyone, and welcome back to another episode of The Art of Space Engineering, the podcast which explores the details and lessons learned behind how missions get to space. So, I've talked quite a bit about my CubeSat Phoenix in this podcast and how we went about developing the spacecraft as a student team at ASU. And really, one of the main reasons why I wanted to create this podcast in the first place was to share the knowledge from our team in a way that's just very easy for people to consume and take something away from. Because the amount that we learned from this project over the course of 5 years from start to finish was just incredible, and it seemed like a complete waste to just keep all of that in my head. So since Phoenix launched, I've actually been contacted by a handful of student teams who are interested in learning more about what was it that made Phoenix successful, whether it be related to the later stages of development or how to best start these projects from scratch. Some have also been listening to the content that I've been putting on this podcast. And, this just absolutely makes my day every time I hear this. It's been very, very humbling to just see that these episodes have been a really helpful resource to others. So thank you all so much for supporting this podcast and passing it along to others. So because of all of this, I've been able to hold what I've been calling mentoring sessions with other teams where, we just chat about what worked for us, what didn't, and we go into depth on a few topics that I wasn't able to cover in my earlier episodes on Phoenix that were done with my team. And since a lot of these are via Zoom, I figured, why not record these and actually make them episodes with their permission, of course. So I'm going to make this a regular series of episodes on this podcast and probably do a few of my own where I just go over common questions that I've gotten via email or other Zoom calls that maybe weren't recorded. And eventually all of this information will be in book form. At some point in time, I have to get a little bit better with my time blocking to actually finish it. There's a lot of stuff written down, but it's not really compact. But that's another project for later. So the very first episode in this series is going to focus on the RF side of CubeSat development, both on the spacecraft and on the ground station side. So I'll be chatting with Jose Pastrana and Joe McPherson from the Rhodes College in Memphis, Tennessee, about just various challenges that we face while working with our UHF transceiver, which is hardware that can both transmit and receive, in case you've never heard that word before. We'll cover how we solve these problems while trying to transmit data from the spacecraft to the ground station side. I'll also go into detail about how we went about setting up the UHF ground station at ASU so that way we could communicate with Phoenix after it deployed into orbit. So if you're looking for advice here, or if you're just interested in learning more about what actually goes into preparing these subsystems for the operations phase, then I hope you enjoy this episode and get some good tips out of it along the way. So without further ado, let's get into it.
Our project actually started about a year and a half, maybe 2 years ago. We've got an alum that gave us enough money to do a CubeSat project. He wants to see us launch a CubeSat. So we attended the CubeSat Developers Workshop last year, the one that was actually in person, and then the SmallSat conference. And so we've made progress along those lines. We've got a mission developed where we're going to be testing solar cells, two different types, neither of which have actually been tested in space. And we're partnering with the Oklahoma University because they have a big solar cell research lab there. So we kind of got that part sort of defined, but now it's really getting into the details of things. And like I said, the ground station is one area. The flight control system is another area. And of course, no one here has done any of that. And we're not an engineering school, so we don't have all of the sort of engineering resources that some schools might have. So that's kind of our background.
So I think a good place for us to begin could be maybe talking a little bit of the content that you have on the Arizona State or the Phoenix website on amateur operations, like all the amateur ops. We, like like Joe said, we're trying to get this two-way communication going, to be able to, send and receive, or receive data other than just voice. And we actually do not have, so we've been reading a lot. Well, we just started, but we've been reading about the terminal node controller, so the TNCs, and how to go about setting that up, because that's kind of like the one piece of our ground station that's missing. And we are also want to fill a little bit with the software that you published on GitHub. So I think a good kind of like, we actually read that tutorial that's also in the resources page from Virginia.
Mm-hmm.
Yeah, that helped us a lot, just to understand what the heck is going on.
Right, because like it says, like there's so many different combinations, right? You could do the hardware one or a software one with the audio card, or just kind of like a bunch of different combinations.
Okay, so just as a quick aside from this interview, I want to add some context to the document that we're referencing here. So there are various setups that you can use for a ground station, depending on what you're trying to do or what RF signals you're trying to decode, and how much you want to be hardware-based or software-based. Now, either way, you need something that can tune to the frequency that you're listening in on and attach to an antenna, and something that is capable of demodulating the signal and decoding the bits inside of it. Now, what demodulation does is that takes the signal that you've transmitted and it extracts that from a waveform that carries your data to its destination. And on top of that, there are also different protocols that you have to incorporate into any packets or bytes of data, so that way you can identify packets based on where they are coming from and whom they are going to. Now, this is a whole episode of its own that I really want to do at some point, so I won't go too deep into the weeds here. No. RF, if you don't know anything about RF is a really neat topic. Honestly, if I didn't do aerospace, I probably would have done something with RF engineering, because this stuff is just so freaking cool. Anyway, so the ground station hardware that you'll see is in the form of radios and terminal node controllers, or TNCs. The radio captures the signal at the right frequency, and the TNC demodulates and decodes that signal. So you connect the TNC to your computer and presto, you can see the bytes of data on your screen, and then do whatever you need to do with the data that you've received. There are also some software-based versions of TNCs which provide a completely free way of decoding data. And they do this for various encoding schemes that are very common within amateur radio operations. Now, the ASU ground station was entirely hardware-based. We had a physical radio, which was the ICOM 9100, and a TNC, which was the Cantronics KPC 9612 Plus. And if you want a reference to those, you can look at the amateur operations page on our website. Essentially, we bought those because one of our faculty advisors knew that they were very common and reliable components based on his experience, and they worked out very, very well for a ground station. As for the spacecraft end, we use the GomSpace AX100 UHF transceiver for communications, which you'll hear referenced in this episode a few times as well. So while we were getting introduced to all of this and trying to understand how to set up all of the hardware and what all of these different protocols were and how they were structured, we came across this really amazing presentation developed by Virginia Tech that essentially goes over all of the different hardware and software configurations that you have to choose from in terms of ground stations, as well as how various RF protocols are structured and what bytes are what. There's a part later in this interview where I refer to a TNC manual, and this is still the document that I am referring to. Now, I really can't stress the significance of this document enough, because it's so important to understand these protocols inside and out, because you may have to back information out of something that you have received, or even put whatever that you're transmitting into a specific format. And if you didn't do it right, then your transceiver isn't going to recognize whatever it got, which is going to make operating your spacecraft a little bit difficult. So this resource from Virginia Tech became incredibly useful to us, so I've put it on the Phoenix website to share with anyone else who may need it. And you can find this under our documents page if you're interested, along with a bunch of other resources that we've put together over the course of the many years that Phoenix has been put together. So that was a very long aside, but necessary context for the rest of the episode, so let's get back into it.
What do you think would be a good first step for us to prepare for working on the flight software? Do we have to wait for all the hardware to get here? Can we start, learning some of that stuff, or base it off somebody else's?
Yeah. For example, your podcast mentions requirements, and one of the problems with writing requirements is you have to have some idea what you're what you're supposed to do.
Right. Well, and your requirements will evolve over time too. So the requirements that are on our website were, they were majorly updated. Like if you go and look back at even our design reviews didn't really show all of our requirements on there, but there's, they will get refined a lot more as you learn more and get more comfortable with the project. I guess, so, okay. So it seems like you guys have a few questions. One is, I guess, any tips that I would have for you guys on just listening for satellites and receiving things through like more of an AX25 protocol as opposed to voice. And then the other is any recommendations I might have for you guys establishing like your own software in order to receive and post-process any packets from your spacecraft when it is in orbit. Do I have that right?
Yes, that's exactly right.
Okay. Let's see, which one should I answer first? Okay, I'll answer the first one.
If we can get that all done in an hour, that'd be great.
Yeah. I'll do my best. And if we need to do like more of these too, with any other questions you have, I'm happy to do more calls.
Thank you.
So, okay. So in terms of trying to listen, so in terms of trying to just listen to spacecraft that are in orbit already, I think I recommended the SatNogs database to you guys. So that's a good resource because on there you can see which satellites are active and which ones have like actually active beacons. And there's a really good community page that will, help you understand how to, or they have decoders on there so you can, I guess, compare things that you get with they have decoded through their database because they do all of the processing.
Okay, so another quick note here for those of you who have never heard about this before. SatNog stands for Satellite Network of Ground Stations, and this is an international network of ground stations that help track and monitor data from spacecraft, both small and large alike. This database is awesome for operators, especially for the early days of the operations phase when you're just trying to figure out where your CubeSat is in orbit. All over the world, ground stations can be set up to track various spacecraft, listen for messages, and try to decode whatever it gets. SatNogs also gives you really good insight into exactly how successful observations were. You can see whether data was collected, if a signal was only seen on a waterfall plot, or if nothing was received at all. You can also see which stations are scheduled to track it next, so you can follow these and keep up with them throughout the day or throughout the week, however you're tracking your spacecraft. You can even register your own ground station there to be part of the network. And there's a great community of people who you can talk to about anything related to tracking CubeSats, ground stations throughout all of this. So when Phoenix was in the operations phase, there were only 2 times a day when it would pass over the ASU ground station, and we could actually transmit commands to it or even hear anything from it. So SatNogs became a very invaluable resource to us because it allowed us to track telemetry over the course of the entire day when we didn't have access to it. So that's a rough overview of SatNogs. And if you're interested in learning more about it, definitely go check out the database. And if you're actually preparing for the operations phase, then I highly, highly recommend playing around with the database and starting to talk to people. If I'm being completely honest, we could not have done the operations phase without the help of the SatNogs community. So if any of them happen to be listening to this, thank you so much for all of your help and for all of the help that you've given to countless other CubeSats who have come your way. You guys really are awesome. Okay. End of mini aside. Let's get right back to the interview.
So when we started trying to listen to satellites with our ground station setup, we were just we just picked one from the SatNogs database and we set up gpredict. Are you guys familiar with gpredict?
Yes.
Yes.
Okay. So we set up, so we had gpredict configured and connected to our hardware. So that was commanding our antennas to point. It was also doing Doppler shifting for our radio. And yeah, so it was basically controlling how the antennas track the satellite and then also how the radio responded to that. And so we basically just picked something from SatNogs and we plugged it into gpredict and we said, hey, track this. And we just listened for something. And it's helpful. I mean, one way you can see if your ground station is tuned is if you get a signal at all when you expect to get one. There's about a 10-minute window-ish when it's at least within range of your antennas, but there's only going to be about 3 minutes of that that's actually usable when the satellite is at an optimal elevation for you to actually be receiving signals, because your antennas are going to have some elevation requirements below which they won't be able to hear anything from the spacecraft. So that's where a lot of that 10-minute on both sides is where a lot of that 10-minute interval gets lost, essentially. So what we did is there was an audio line in our ground station radio, and we plugged the audio line into our computer, and from decoding the audio, there are software that will just show you, at least if like you've gotten a spike, or it will show you the waterfall, and then you can see, okay, this is where I've gotten a signal. You won't know what's in that signal, but you will know that you've at least gotten a signal. So with things like this, I would break it down in two ways. One is just making sure that you can receive a signal at all, because that's going to be a big part of of you tuning your ground station. And then after you know that you can receive signals, then trying to modify such that you can figure out what's actually inside of them. And so for PhxSat, we have our specific decoder, which is our GitHub software. And so basically, once you know you can receive signals, then you can set up our code and link that with your ground station setup. And then if packets come in on your receiver, it will just go to the TNC, then over USB into your computer, and the software will process it and show you what's there. A nice thing about the SatNogs database there too is that since you can look up what satellites are active, a lot of these have their own websites, and some of them may even have their own decoders, similar to what we have. I can't think of, it might have been Spooky. It's like SPOOQY, something like that. I think that might have had another decoder, which I think you might have more success with, trying to decode signals, just considering that PhxSat is just because of the anomaly we have with PhxSat, and so the beacon's not, it's not currently active. So, so in terms of listening for satellites, I would start off with just picking one from SatNogs, or well, not picking one, picking multiple from SatNogs, and then tracking them and just seeing if you get stuff. And there are, another thing too, is that there's a lot of other amateur radio decoders that will just decode the signal itself, and it will be in hex. Like you won't be able to see things like what's on our website where you see a decimal value. Well, no, it did show. Actually, I don't remember if it showed decimal or if it showed hex. But it would at least, like on our website, it was like, oh, okay, the first index is this decimal value and that corresponds to this. And so if you actually got a health beacon, you could kind of go back and check that and see what it was. But there are other amateur radio decoders, and I can try to find examples of these and send them to you, where once you do get the signal over the audio line, it will actually decode that audio for you. Does that make sense?
Yeah.
Okay. Okay, I didn't know. I haven't had to describe this yet to other people who aren't familiar with it. So if I'm being confusing, please let me know. But it's like there's like a drop down list, and you can select, oh, this is the modulation is GMSK, baud is 9600, and it will, when you get a signal, and it will decode what that's supposed to be. And we got that working, I think, with maybe a few of the satellites in the SatNOG's database, but it didn't work for our specific transceiver for some reason. So you might have success with some and not with others. It might depend on how their stuff is set up. But the nice thing about SatNOGs is that because you can look at all of those satellites on there, you can look at exactly what their transceiver characteristics are. So what their baud is, what their frequency is, and what kind of modulation scheme they're using. And then basically set up that decoder software so that way it's going to do that correctly. So that's nice.
Another brief aside here, just to give some additional context to what I'm talking about. So these decoders that I'm referencing are the software-based TNCs, which you can configure to help you decode whatever type of signal that you're listening in for. So things like the baud rate, modulation scheme are all components that enable you to actually decode these signals properly. Software-based TNCs have also been demonstrated to have worked with AX100 transceivers. It didn't work for ours, I believe, because of the way that our packets were structured specifically. We had a little bit of trouble figuring out exactly why that was, but it was definitely very specific to Phoenix and not to GOM-based hardware. So I just want to put that disclaimer out there so that way, you know, you don't think, oh, okay, if I buy this, then I potentially can't use these resources, because that is not necessarily true. Definitely, you know, talk to people about it. If you're considering buying like a GOM-based hardware, then using like a software-based TNC, definitely talk to people. Definitely talk to your vendors about that kind of a setup, and just see if they have any type of experience or any additional input on that too. Or even get in contact with other CubeSat teams who have potentially used the same hardware as you, so you can see if your particular setup has been done before and has proven successful. I think I've said this before, but experience is everything with these projects, so definitely reaching out to people is really the best way to just understand if your approach is going to be a successful one once you actually get your spacecraft to orbit. Or even if you're just setting up like a lab-based ground station for, you know, doing some initial testing. Either way, highly recommend just going out and talking to people and trying to get a second opinion. Now, to touch on this topic just a little bit more, we did play around with a handful of software-based TNCs when we were preparing for the operations phase, because we wanted to provide people with different options for listening for Phoenix after it had deployed. You know, not everyone has the resources for or wants to have a fully hardware-based ground station setup. I mean, our ICOM alone was a few $1,000s, which is pretty expensive. So on our website, what we did is we listed all of the physical hardware that our ground station used, but then we also provided a software-based setup that would allow people to at least receive packets, and was also something that we had proven reliable ourselves. So in terms of the software-based TNCs that we did play around with, we found that Direwolf was actually a really good resource. That's linked on our website under the amateur operations page if you're interested. It also goes really well with SDR Sharp, so you can set both of those up to receive packets and then decode what's actually inside of them. MixW was another one that we found. That's mix and then the letter W, all one word. And that might also be useful in decoding packets depending on what you're transmitting. A really nice thing about MixW is that it also displays a waterfall plot, so you can actually visually see packets coming in as you're receiving them. Another thing that it does is that it also accepts audio input. So one thing that we actually did when we were playing around with this is that we took the audio line from our radio and plugged it into our computer, and then used the waterfall plot to actually, you know, see packets coming in over that frequency. There's other software out there such as AGW Packet Engine, which interfaces with the sound card on your computer to receive packets. However, you do have to be a little bit mindful with the sound card-based packet engines, because some sound cards do not have the capability to properly decode a packet if it's transmitted at 9600 baud. So this was actually the case for our computer setup when we were trying this out. So while this is still a great and well-documented resource for other systems, this didn't work for decoding packets for Phoenix or spacecraft that were similar to it. So with that being said, if you're operating a system that is similar to Phoenix, that is, you know, it's transmitting at 9600 baud using GMSK modulation, then I would personally recommend trying out Direwolf, just because it works really well for different applications, was pretty easy to use once you read the user's manual, and there are a ton of other people out there who use this as well. So I definitely recommend checking that out if you're interested and seeing how that works for you. And on that note, let's segue back into the interview.
If you can, in terms of when you get hardware, one thing that's going to really help with this a lot is getting a setup in the lab that you can use for decoding with just like the hardware that you're using, the hardware that you intend to use in the spacecraft. So us listening for satellites really came much, so let me back up there. So when we were preparing the ground station for Phoenix, we did a lot of testing in the lab on a benchtop setup. Because when we got our ICOM radio and the TNC, all of this was like brand new out of the box, and it had never been set up with anything before. And so there was a lot of tuning that we had to do with settings in order to figure out which knobs to turn such that we could receive a signal at all. Just learning how to operate with those was not very intuitive at the start. And then once we started receiving packets, then what we had to do next was we had to, we were having significant packet loss issues. So it was like we had, I think it was 70% packet loss or something. It was very large. And so we were getting packets, but it's like, this isn't really, your packet loss rate should be much, much higher, like above 90% for communicating with anything, especially in a lab setup where it's like, my radio is here and my ground station is here. Like there's zero link latency there.
Right.
And so there's a lot of debugging we had to do with that. And so the faster you guys can get a lab-based setup to where you can just constantly transmit packets and just, work with the settings until you start doing stuff, that is going to help you a lot. One thing that we realized, so this was, so the packet loss that we were getting came from the fact that the radio ended up clipping our audio. So it was, or not audio, I'm sorry, it ended up clipping the signal. So when the packets came in over the radio, they were getting clipped. And so we were losing a lot of the packets that were coming in, and that's what, created that massive packet loss. And then we solved that, and then our packet latency was like 95 to 97% or something like that in the lab. But yeah, it was a lot of work, and it wasn't in it. It took a long time to set that up. So, so getting a lab setup going is good. And to go off of that, the way that we kind of worked on setting that up incrementally, so we didn't start off initially with the final ground station software that you see on GitHub is largely derived from what went into our flight software. So basically we made, and that was also mostly just because of the way our flight software worked with how we were with the NanoMind, since GomSpace has their own firmware software that works with the NanoMind, it was important for our ground station software to basically mimic that, so that way we could communicate, we could get packets to the OBC properly that it would understand, and that we could decode what we were getting back from our OBC. So the whole setup that's on GitHub now came much later. And basically we just kind of took our flight code and copied it, and it worked pretty well. That's not to say that everyone should do it that way, but that's what worked really well for us. And it's just based on how our thing was designed. But when we started off with the ground station, our flight software was not that far along. And so basically with this, I would also recommend that you start doing this more incrementally too. So and just starting off very simple and trying to break it down, and then adding more complexity on it as you get more familiar with what's happening. And the TNC manual will hopefully help you a lot with this. But we started out by just, so we just had a simple Python code. And the Python code essentially, it would send packets to our transceiver, and it would request information back from the transceiver. So basically, to make sure that we this was how we established a link was, okay, so our Python code is sending out a packet. So if that's working properly, we should see a packet go from the computer to the TNC and then out the receiver. We should be able to see that visually using like a spectrum analyzer. Or we had a signal hound which showed us the spectrum, and so we could actually see, oh, okay, hey, look, something was transmitted. So that's the first step, is just, okay, all of these things are connected. I can get a packet from my PC through my TNC and then out through my radio. And then the next step of that was, is this actually being received by our transceiver, for one? And then two, the next problem after that, after just seeing, oh, okay, if this is even received, and we could tell if it was received because we could just connect directly to our transceiver and then see, oh, hey, look, it actually got a packet. Whether it understood what was in that packet or not was a completely separate issue. And that took more debugging. So step one is just getting a packet out of the radio. Step two is making sure it's actually received by your transceiver. And then step three would be making sure that the transceiver can see the packet, understand what's in it. So like you've structured that packet correctly, essentially, and then do something with it. So with the simple Python code, our transceiver had this feature where if you sent it a packet that was like structured in the right way, the transceiver would send back its health data. And so basically we set up this Python code to just send out this command in hex. And then if that went through the entire chain successfully, then the AX100 would repeat back with its health data. And if that happened, then we had another part of the Python code that, should have gotten that in from the TNC and then just displayed it. And then we looked at what came back, we decoded it, we saw if it matched or if it was, completely wrong, and made sure we understood what was coming from it. And once we had done all of that, that's when we knew that we had a complete link from our spacecraft to our ground station. And then after that came the fine tuning with all of the packet latency issues. But yeah, that was the first basic step that we tried to do, was just isolating that system as a whole and getting that to work.
You guys opted to use a hardware TNC. Any reason you did that over software?
There are software TNCs. Actually, the decoder software I was talking about is a software TNC, essentially. There wasn't, not really. We didn't do a big trade study over it. So our faculty advisor, Danny Jacobs, he happened to know of the ICOM, actually Judd and Danny, so both of our faculty advisors, their work is not on like urban heat island research. We're just doing stuff with urban heat islands. Like they both do radio astronomy. So and Danny in particular has had experience in the past with CubeSats and like amateur operations. So he knew of the ICOM and he knew of the TNC that we used, or we just picked a compatible TNC, and he was like, here you go, it's your ground station. So we didn't do a huge trade study there, so I don't really have an answer for it, or how, an answer for how good software TNCs are with a hardware-based one. I guess the nice thing about a hardware trying to remember, I don't want to say anything that would. So I guess the software TNCs do have like those decoders in there. And sometimes those work really well. Sometimes they don't. For the most part, it works pretty well. Like I think a lot of ham radio operators who have moved more to a software-based platform use like TNC software, and it works pretty well for them. Since we didn't work, I guess I'll say it this way. Since we didn't work with it we never tried hooking our ground station software up with the software TNC, so I can't say how that interface works, and if you know, like setting your code up so that it sends, either way you would be sending it to a port. It would either be a virtual port. I think a lot of that software you have to pay for. There might have been one that was free. I don't remember. But yeah, but that's how you would connect those, is you'd have to send it to a virtual port, versus if you bought a hardware TNC, you would be sending it to a COM port. But I think both should work in the same way.
Yeah, I've got a mini setup where I'm working with one of the AMSAT fun cubes, trying to decode their stuff. We've actually got that to work, but a lot of virtual cables. You know, there's software called virtual cable, and you know, you lets it route it as if it was going through all these external cables, but it's all in software.
Right. And I don't remember too. I also don't remember if the icon like could connect over USB, because yeah, because I think like people who use software-based TNCs like also tend to use SDRs, so it's a bit easier to connect the two. And I don't know how easy it is to connect hardware to. But I think people do that though. Okay, I'm going to stop rambling about a topic that I'm not an expert on. Actually, okay, a really good group of people to ask would be reaching out to the SatNogs community, so that there's a really awesome community of people on there who are very willing to help, you know, student teams who are working on CubeSats get a ground station set up. Another thing I would recommend is actually contacting the amateur radio community. So there's like an email chain that you can get on the AMSAT just email chain, and it's just like a listserv. And so if you send an email out with you know, to a specific topic, there are people who just monitor that, and they will answer your questions. And then there's a database with like all of the emails that anyone's ever sent out, so you can peruse that to see if there are any similar questions. But the amateur radio community they're a very good source for asking questions like this, because there's a bunch of people who play with this stuff. And that's where we went for a lot of our debugging, and well, our debugging when we were preparing for the operations phase. It's also good, you know, when you do launch, to reach out to those communities. So reaching out to the amateur radio community and reaching out to the SatNogs database and saying, we have a CubeSat that's launching on this day at this time. You know, if anyone's interested, please listen for it and try to help us find it, because the big task just after deployment is, okay, is my CubeSat working? Like, has anyone heard this beacon? And then once you find out that, then, okay, they've just deployed 10 CubeSats, which one is ours? So that's a whole mess of problems. But yeah, so both of those groups could probably answer your question on how to set things up.
Super.
Were you guys considering getting like physical hardware, or working more with like SDRs and like these software-based TNCs, or do you not know yet?
Like I said, we've got a ground station, and we've managed to communicate with satellites, but only,
I'm sorry.
only through voice. And we've done that actually with our ground station. We've made our own handheld antennas, use SDR dongles, you know, so we've gone at it a variety of different ways, and that's all been a good learning experience. But now we need to do the data, and one of the problems we've run into is we ended up purchasing an ICOM 9700 radio, but that radio does not do 9600 baud.
Okay.
Which is a real problem. And
you can't send it back.
Well, we can't send it back, but it might end up on eBay.
Mhm.
Um,
Does it, well, what does it do? Does it do 4,800?
12. It'll do 12
Oh, okay.
up and down. And it's, there's a lot of disappointment in the ham radio community with ICOM because, this is the new model on top of the IC 9100. And yet the 9100 has more feature than
Mhm.
this new radio. It's a great radio otherwise, but so from there, I've been thinking about using something like, we're just looking at this, the Lime SDR
Okay.
as sort of our radio, or even going and using a 9100. Although it's hard to find them new right now. And then as far as the terminal node controller, I've looked at that Cantronics, and seems like a lot of people use them, so it's probably a reasonable choice. There's always a trade-off. Personally, for some things, I would prefer hardware over doing things in software, and that is probably one of those areas where I think I'd rather have a hardware terminal node controller.
Yeah, it is. I mean, we didn't dabble a whole lot with SDRs, but from what we did, it's just like using, not GPredict. Forget what like GNU radio, like just trying to like install that properly and then use it gets really difficult. So, yeah, I would also agree if it's possible for you to get a hardware radio. I think it will save you a lot of grief.
We totally know what you mean. We've been, like experiencing that. Yeah.
And I went to the gamut on software too, GPredict and SAT PC32 and Orbitron, and I mean, there's a whole host of them out there.
Mm-hmm.
So between the two, we've got SAT PC32 running and then GPredict, and we're actually in the process of looking at the GPredict code itself,
Mm-hmm.
trying to use that as maybe a learning platform, because we don't have we have a very minimal base of people who know how to program in C.
Mm-hmm.
And our flight control software is going to have to be developed in that.
Mm-hmm.
Our hardware is coming from ISIS-Space.
I would say, that's another good thing to reach out to the amateur radio community on. I mean, if there was, like, if you could install GNU radio properly and someone was able to give you code that was like, hey, this will decode signals at 9600 baud with the AX25 protocol, and you can test it and it works fine and it decodes what you need it to. I mean, that might be one way to go.
Yeah.
But like developing that from scratch is like way beyond what I or even Danny and Judd, know how to do. We don't have a lot of people, at least I don't know anyone at ASU. That's not to say that there isn't anyone at ASU. May have an old professor who knows how to do it, but there's not a very large community at ASU that uses GNU radio. So I guess kind of going off of that.
Is your decoding occurring in the terminal node controller, or?
Yeah. Yeah, so that will demodulate the signal and decode it for you. Mm-hmm. So I guess because your other question was, what can we do to prepare the ground software now? I would say, I mean, your ground, it's really hard to, I would say to start, just try to like just see the hex data, get it to where you can see hex data, and starting off with like simple Python scripts, just so that way you can get the interfaces down, because that's really how we broke that up. Was first, okay, how do we develop the software such that we can actually interface with our hardware, and then the actual code that we made for not like decrypting the hex that came in over the radio, came much later once we had an established packet structure, and we could say, okay, so the first X number of bytes is going to be the AX25 header, and all of the headers that are associated with our packet, and then everything after that is the data, and then the very last 4 bytes is our checksum. So once you have an established packet protocol like that, and you know exactly how that packet should be decoded, then that's when you can start getting a lot more specific with your ground software and saying, okay, so this is coming in, this is how I need to process this, so that way we strip the AX25 header because we don't want to look at that. That's not important. We just want to see our data. So that's how we broke that down. Is just starting out simple and then adjusting it as we learned more. And then once the system became a lot more robust and we started trying to develop ground commands to say reset the spacecraft if we needed to do that. So like maintenance commands, similar to the ones that we talked about in the podcast. Once we had that, then we could start actually making ground software commands with the proper structure, so that way the satellite would recognize that, understand it, and could do something with it. So that's, for the early stages of ground software, that's my recommendation. And then once you guys actually get to the point of where you're sending packets back and you know what that looks like, I think you'll know what to do with your ground software. It will be, you'll know what to look for. And then I guess, well, it's a kind of, yeah, so you'll have that. And then the last part is, okay, how we have all of this data, how do we visualize it? And so with that, we intended to have a Python script, which could basically, when packets came in, so we had a file, we had like a telemetry file, which would then get broken up into packets to be transmitted. And then once the file was fully received by the ground station code would reassemble that file. So that way we had everything the same way it was on the spacecraft. And then that file contained all of our health data. And then we would have a Python script, which would read that file of health beacon data that we got, and would parse it, so we could do things like plot the battery temperature over time, or or plot the temperature of various components over time. So that was one way that was easy for us to do that. Did that answer your question for the most part about setting up the ground software? Okay, cool.
Definitely, yes. And just a very small question about that. We've been reading about the KISS protocol as well as the AX25, and since they work together, from my understanding, because what the AX25 are basically the packets, right, and the structure of those packets. I would say it would also be worthwhile to kind of like get up to speed on how that works, and right, and how they interact. It seems like, okay, I think I answered my own question.
Yeah, I would, so in terms of how the AX25 protocol is structured, we looked at the TNC manual, and that's how we really understood how the AX25 protocol was structured and how the KISS protocol also factored into that. So I would say so AX25 and KISS, I will say this, they're standard protocols that are used by the amateur radio community. It wasn't, so like we didn't do a huge trade study for like, oh, which protocols do we use? They are standard, so it's good to use those because you'll have a community of people who can answer your questions, and it's a well-known common structure that's robust and is documented very well on how all of those interact. But also our radio is configured with specific settings. So like on board the radio, if it was, because of the software that was already on there from GomSpace, it would take your data and then package it up in like the AX25 KISS protocol and then send it out. So we didn't actually have to do any of the AX-25 and KISS structuring on the spacecraft, but we did have to learn how that would work so we could implement it on the ground side properly. Yeah. So understanding those will be useful, and that's why we used AX-25 and KISS on Phoenix.
That makes a little bit of kind of like this farther away question. The operating system of the onboard computer that we'll be getting in January will be running on FreeRTOS. And we were wondering if you guys used anything related to FreeRTOS.
Mm-hmm.
Do you have anything to say about FreeRTOS, I guess? Because we are also putting a little bit of weight on, okay, let's read up on that, let's get ready for that, but what is your take?
Yeah. Actually, if you're more interested in the specifics of FreeRTOS, I think putting you in touch with, so like Craig Knobloch, who is on the podcast with me, would know a lot, could talk a lot more to that. So we used FreeRTOS and NASA's core flight system as our kind of like flight software architecture. I can't say a whole lot about, since I don't have a huge software background, I can't say a lot about FreeRTOS. So I can see if, and Craig will probably be willing to chat with you about this, and he's on East Coast time, so I think his time lines up with you guys. So I can see if he'd be willing to talk to you about that and answer any questions you have about just getting like the flight software set up.
That'd be really cool, because we really don't know anything about it. We're kind of like, again, seeing how we can get ready to explore that or get up to speed with it, and I guess know where we will take that, as in, do we actually need to become professionals in this, architecture, like you say, or is it also overkill for us? That's kind of like my own question. So that'll be really cool.
Okay.
Thank you.
Go for it.
I've heard it's a good sort of framework to work from, but then you really have to sort of assess what of it is really applicable to what you're trying to do. I talked to some of the people at Morehead State at the SmallSat conference, and they said it's good, but it's not out of the box by any stretch. And of course, they're doing bigger missions, but he said there's still an awful lot of work you have to do with that to make it work with whatever your CubeSat is. So that's right in line with what you just said. But it is a framework which, for us right now, just even looking at the FSW applications and breaking it down by this command ingest and the ADCS system. Of course, we won't have a camera, but just having those chunks sort of out there, giving you something to think about anyway.
Yeah, you guys you're doing the right thing by reaching out to people and asking them about their experience and what they feel they did correct and what they didn't do right. And so I think, if you reach out to more people and you find what they did, through that, you could probably find a very good architecture that's a good architecture for your specific mission, because every mission is unique. And so some things that work for one aren't going to work for others. And so, it might be that you find something better, or it might be that, a lot of people are using FreeRTOS and there's a lot of things wrong with it, but it is a decent application to use. And so working with people, you can better understand it and then apply that for your mission. So I'll see if I'll talk to Craig and see if he has some time and he can give a much better input on that than I can.
Awesome. Our selection of RTOS is really driven by ISIS, because we could use CubeOS, but the software libraries that ISIS has that works with all their hardware has been certified to run on CubeOS, but it is on FreeRTOS. So it's like well, I guess we're using free RTOS, aren't we? But that's not a bad thing, because at least the software libraries and the hardware that is being provided by ISIS will hopefully work together.
Yeah, it will. And the nice thing about that too is that using components that have their software built into them is that through seeing what there's these people who have worked on space missions before, and then adjusted their software based on what works well and what doesn't. You will find things in there that you didn't think to incorporate, or other features that would have taken you a very long time to incorporate or been very difficult. So like we didn't really use this, but the AX 100, for example, features for you to like deconstruct and reconstruct files, for example. And so, and that was something that we'd even thought of when we started working on our communications link was, oh, okay, how do we, how would we even do that? Like completely deconstructing and then marking them into all of these packets. And if we don't get all of the packets back in one pass, how do we write software such that we can re-request packets so that way we can, complete a file? We don't have to always restart from scratch with downlinking this file. And so we were able to take a lot of ideas from just looking at the software and modify them. And that may, I guess I'll mention that too, because if you can, there may be some areas where you don't have to feel so boxed in by the software that they use on their platforms, and you can write your own code that still interacts with like their firmware, but you can modify things such that it's easier for you to work with and is better for your unique application.
That makes perfect sense. I'm sure, like you say, reaching out to different people that have had experience with that, these communities are pretty cool because they're willing to share a lot of that.
Well, we're at our hour. And we want to be respectful of your time, and actually now we've got more things to go back and think about. And, I mean, if you're willing to
continue this conversation.
Continue the conversation.
Yeah, no, it's I mean, honestly, I think these are fun. It's nice talking with people and telling you guys about all the ways that we broke things, so that way you don't break them too. But yeah, I mean, the point of CubeSat project should be that other people suffer, so that people in the future don't have to do the same thing. We didn't talk to a whole lot of other teams actually. We kind of just we're like, okay, we have all these fires to put out. How do we do that? And I don't know. It was always, maybe it's because I didn't really reach out to people, but I was always just felt like, why isn't there like a database for this kind of stuff? Right. Like how many people have built CubeSats? And so, yeah, if you guys want to keep doing this, I'm happy to chat.
Okay.
Super cool.
Well, we certainly appreciate your time. It's been very helpful for us.
Good. That's good.
I think we have a very defined next step, which will be to set up this transceiver and TNC, TNC structure. I just have one last question, super quick. Would you say that it would be helpful to split the software team from the communications team? Do you think, or I guess my question is, how was your structure? How many people were? I know, like you mentioned, and we're experiencing this too, that the amount of members in the team is fluid. It just changes throughout the semester. Classes get in the way, finals, breaks. So I'm sure there's not a definite number, but did you have kind of like two well-defined or separate groups to take care of communications for all this work versus software?
Yeah, and we can go more into depth on like team structure in another conversation if you want to, but we did have those separate. So we did have a comms team and we did have a software team. However, both need to work very closely together because your software, so like our software team had to learn how the AX25 protocol was structured, because if you're getting a packet and this packet has, so if we're getting a packet from the spacecraft, and the packet structured in this way, the software, whoever's developing the code has to understand how that's structured, and they have to understand how to break it down so we can just look at the data that we need. So, and yeah, that too, and in programming applications, hardware specific applications, like we talked about in the podcast, it was very important for the flight software team to work with the subsystem leads, or well, they ended up being the subsystem leads, but really it was just a person who understood the hardware very well, to understand how that hardware worked, and then understand what do I need to get from this hardware, or how does my application need to be structured such that, you know, it incorporates all of the features or requirements, they will eventually be requirements, that we need in order to make this mission successful. So your software person will end up understanding. Yeah, we had a dedicated software, or a couple of dedicated software members to one specific hardware application. And so it was that software person's job to also know how that specific component worked and work with the subsystem lead in order to better understand how that component worked, because the subsystem lead would have been the person who had done like qual testing with that hardware, and you know, through looking at the data sheet and you know, just testing it out to make sure it worked, better understood how that component actually operated. And so those two working together were able to kind of help more of the software side come together when we did that for every component. So we separated. So software team was its own team. Our software team also ended up developing the ground station software, but that was basically because it was more, the software ended up being more of a replica of our flight software. We had a comms team, we had an EPS team that understood the EPS system and made sure that things like, they also designed our interface board with all of the proper features it needed. So all of the proper data and power routing that we needed. Our ADCS team worked with the ADCS and made sure that the firmware was correct with that, and that we understood how to command the ADCS so that it would point and operate the way that we needed it to. Yeah, so we basically, for every subsystem, there was a team that was responsible for just becoming very intimate with that hardware, and then working with software to help develop applications. But at the same time, it's important that you know, you have like your systems engineers who understand how all of it works, so that way they can help direct people where is necessary. And on top of that too, it's also important for really anyone on the team to just understand the spacecraft outside of their own subsystem, because when you have multiple people who understand the system, you have multiple people who can find problems, and find them early on, or help the systems engineers direct other tasks and what have you. So the spacecraft will come together much more efficiently with the more people who understand how everything works as a whole. So I would say, you know, first focus is always on the subsystem, but second, if they have time, and you will find dedicated people who will stay and who will get, you know, really into it and just want to learn everything. Even if you're experiencing a lot of turnover, there will be people who will do that, and you guys will get it done, and it will work, and it will be awesome. So yeah, so that's the advice I would give in terms of team structure, and who has to understand what. And it's important to have a lead for each subsystem, or we found it important to have a lead for each subsystem, you know, someone who was responsible of just kind of managing the tasks for that individual subsystem. But, you know, really at the end of the day, it's good to have some sort of hierarchy just so that there's order. But at the end of the day, really, you're just a bunch of people all programming or working on a satellite. And so like we just kind of sat in the lab and we coded or we tested, and there, you know, it wasn't more towards the end, we did that a lot more. And so I would say breaking down, even though there is a hierarchy, breaking down a lot of those, I guess, I don't want to say barriers, but just like,
Not isolating.
yeah. So like, you know, working, even if you're working on different subsystems, working in the same space as much as possible. It's really going to help with transparency, and it's really, which it's going to, bring you guys really closer together as a team, but also make sure that everyone ends up understanding the system as a whole a lot better, because you're all there, you all see what happens. And you can overhear conversations or just ask people what they're doing, and it will help a lot with that. I know that's very difficult to do with COVID, but even like Zoom meetings, if you can do them, I don't know, maybe awkward, but it's better than nothing.
For sure. And it even gets you on that different headspace to, get to work and collaborate. For sure. That makes perfect sense. And we'll make sure to tell our team, and I'm sure we to start giving that idea. Yeah. Great, for sure. Awesome.
Well, and that's all for today's episode, my fellow space nerds. I want to extend a huge thank you to Jose and Joe for letting me use this recording for my podcast so that I could conveniently share our experience with all of you guys as well. I hope you found this informative, and if you have any questions about our experience in working with communication systems or anything else, please feel free to reach out, and I'll try to help as best as I can. If you've been enjoying this podcast, don't forget to follow The Art of Space Engineering on your favorite podcast platform, like it on Facebook for further updates, and I'll catch you all in the next episode. Here's looking forward to future adventures and the lessons learned from them. Cheers. Sarah.